Okay, hello everybody. It is my pleasure. Welcome to LRVS 2021, and it's my pleasure to introduce Greg Livingstone. He's the Chief Innovation Officer of Fluitec, and he will be discussing learnings from benchmarking turbine oils. You can find out more about him and connect with him in the speaker profiles. And at this point, you should see Greg's code, and I'm going to be removing that, and I'm going to get rid of here, get me off the stage, and bring on Greg promptly. Here we go. Enjoy.
Good morning, everyone. It is a pleasure to be here, and give me one moment here and I will share my screen. Excellent. Well, it's a pleasure to be here. Thank you very much for coming to LRVS, and it's an honor to be able to present again here this year. All right. So today, I will be talking a little bit about benchmarking turbine oil. So what actually does that mean? And what are some of the things that we've done or learned about this over the years? All right, a quick outline of what I will review. First off, what turbine oil should you buy? And actually, why that question's a little bit hard to answer. Secondly, I'll talk a little bit about our benchmarking initiative and most importantly, the meat of this presentation are seven key takeaways that we've learned from benchmarking turbine oils, and then I'll wrap things up with a conclusion. All right, let's get started. First off, let me ask you a question. You have two different turbine oils here, brand 1 and brand 2. Which one should you buy? Okay, so you're looking at two different spec sheets here. You're trying to compare them. They're both at ISO 32, and maybe a little change in brand 1 has a little higher viscosity index. They both meet spec. Brand 2 actually has a higher RPBOT. Maybe that means longer life. Other than that, they all kind of look the same. The specs are somewhat indistinguishable. Both these oils meet your OEM specification. Should you use the same oil that you're currently using, whether or not you have problems with it? Should I just buy the oil with the highest oxidative stability, the highest RPBOT value? Or unfortunately, what a lot of people select is, what is the cheapest oil that I can get? So please don't fall into that category. But the bottom line is that just by looking at the two spec sheets on turbine oils, you really can't tell which one is going to provide the longest life or highest performance. So now we get into the world of benchmarking, and this problem was presented to us about a dozen years or so ago, and we thought, well, why don't we set up an experiment to see if we can at least start to benchmark different turbine oils? And before you could set up any benchmarking experiment in the lab, you first have to know, how does the fluid actually fail in the field? So in the world of turbine oils, the failure mechanisms there's all sorts of different mechanisms that will cause the oil to degrade, but ultimately the oil will fail for one of two reasons. The antioxidants become low, the oxidative stability drops. Once a fluid hits about 25% of its initial antioxidant value or initial oxidative stability value, then it's time to change the oil. So that's one reason. Number two is the development of sludge varnish deposits. So if we have the ability to accelerate oxidation and measure those two parameters, it can give us a pretty good idea of what actually will perform well in the field. So we set up this experiment called the Turbine Oil Performance Prediction test, or the TOP test. And this test has, we've been running this for about a dozen or so years, and it's actually evolved a little bit over time. We used to run this for 6 weeks. Now we have been running this in the latest iterations for 12 weeks. And essentially what we're doing in this test is putting the oil in a solid block heat temperature bath at 120 degrees C, and we're bubbling air through it while the oil is immersed in, or we have catalyst immersed in the oil. Then we pull samples every 3 weeks. One of the 4 glass test cells we'll pull every 3 weeks and perform some tests. So we want to look at the oxidative stability, and we want to look at other things, viscosity and MPC, what the fluid's ability to generate deposits are. So we've learned a fair bit over the time, but I'll tell you, the very first time we actually ran this experiment was really interesting because we had a brand new turbine oil. It had just come to the market. It it was a lot more expensive than any other fluids that were being used in the field. And so we were pretty excited to try to test this. And after 5 weeks, this is actually what the MPC patch looked like. I mean, it failed miserably. And if you just selected the oil based on the spec sheet, well, the spec sheet was brilliantly written and talked about the unique additive system specifically designed to stop varnish problems in gas turbines. The best deposit control turbine oil in the market. It looks amazing until you actually run some tests. And so one of the things that we have actually learned over the years is that not all turbine oils are created equally. There's actually a pretty significant difference in formulations. And the other thing that we've seen is that there's actually been a tremendous evolution of turbine oils. So the example that I just showed was from a Group 1 formulation. And many years ago, the vast majority of turbine oils in the world were Group 1s. The Group 1 oils today will not compare, especially in a thermally stressful environment such as a gas turbine, to some of the latest formulations. And even turbine oil formulations 10 years ago will not perform nearly as well as the most recent ones today. So we really have seen an evolution in the turbine oil world. Okay, so let's look at some of the top key things that we have learned here over the last dozen years in running this test. A couple of these things are actually going to be pretty obvious, hopefully, to you, but maybe there's some new things here as well for you. The first one is that oil color is not related to oil condition. So those of you that have dealt with lubricants for a long time, you likely know this. But all the time, I hear in the field, someone will take a sample of the oil. They're like, "This is really dark. I need to change this oil. It's about time to change." And in fact, it still may have a lot of life left in it. So if you look at sample A and sample B, these are both samples that we have pulled or what the fluid looks like after 12 weeks in this accelerated oxidation test. So they both look pretty dark. However, pretty significant differences in terms of deposits. Oil B generated not only a high MPC value, but a pretty significant stain here on the test cell, on the glass test cell. Whereas oil A, virtually no deposits either on the glassware or on the patch. So you cannot tell the condition of the oil just based on color. Number two, hopefully this is obvious to you as well, but the initial RPBOT value is not necessarily indicative of the performance of the fluid. And so many years ago, when turbine oil formulations made the move from Group 1 to Group 2 oils, you would see RPBOT values that were 400, 500, 600 minutes suddenly would be 2,000 minutes, much higher. And so some people would make a correlation that this oil should last 3-4 times longer. In fact, it doesn't work that way. And so in this case, we're looking at two different oils. Oil A, the initial RPBOT value of 833 minutes. If we kind of trend what the RPBOT value looks like over the course of the test, we have a nice slope downwards here. Compare this to oil B, initial value of 374 minutes. One of the hints on this is that this is actually a synthetic fluid. So this synthetic fluid actually experienced hardly any drop whatsoever in RPBOT value. What oil is going to last longer? What fluid will hit 25% of its initial RPBOT value first? Clearly the first one. So initial RPBOT value is not necessarily indicative of the performance. We like to think of it performance in terms of RPBOT retention. I think that's more of a how an oil is going to hold on to its RPBOT value or its oxidative stability over the life of the fluid. Number three, the RPBOT retention actually doesn't really correlate to MPC. And so here we have another couple cases, oil A and oil B, both a little oxidatively stronger. Oil A is incredibly oxidatively strong, starting with a 2,800 minute RPBOT value. Over the course of the test, it dropped to 2,600 minutes. So it had phenomenal RPBOT retention versus this oil B here that started at 1,100 minutes and dropped down to 450 minutes. So oil A certainly looks like it's going to be a longer lasting oil. Is it going to perform better from a varnish potential perspective? Maybe not. So in fact, at week 12 here, we can see this is a fairly dark stain. And in this case, even though the antioxidants depleted a little more quickly, no evidence of deposits whatsoever. So RPBOT retention doesn't necessarily correlate to MPC value. Number 4, this is somewhat, to me, this was somewhat fascinating, but different turbine oil formulations will degrade differently at different temperatures. So what we're looking at here is a comparison of 13 different turbine oils after week 6 and what their glassware looks like, what the test cell looks like. And you can see a pretty big difference in performance. Some generating a lot of deposits and others generating no measurable deposits whatsoever in the glassware. And then what we're looking at here on the bottom is a really, really accelerated oxidation test. In this case, we're beating the oil up at 180 degrees for 5 days. And in fact, even though it's only for 5 days versus 12 weeks, there is still several times more oxidative stress happening here in this test. And you can also see, based on the degree of the deposits that we see in some of the formulations. So here we have oil A, which actually didn't perform that well or didn't benchmark that well compared to the other formulations at 120. But actually at 180, it actually benchmarked fairly well. And compare that to the next oil that actually seemed like it performed, or at least it benchmarked really well at 120, but you heat that up a little bit more and it's generating a lot more deposits. So different formulations will in fact degrade differently at depending on the temperature zone that the oil's facing. Number 5, viscosity is seldom an issue, and we often use the phrase that viscosity, and viscosity are the 3 most important properties of an oil. So viscosity is really important. It should be a critical part of your condition monitoring program, because if the viscosity goes in the oil, now you'll have some pretty significant issues. The other thing we know is that oxidation results in this accumulation of these polymeric high molecular products that actually can increase viscosity. And however, what we actually see in the real world is that viscosity is really never an issue in the vast majority of cases in turbine oils. If you have a viscosity issue in a turbine oil, either something has gone really, really wrong, you have extremely high amount of heat that's hit the oil, or you've inadvertently blended in another product, or every once in a while you'll have a formulation that in fact the viscosity will increase. And so having the ability to run benchmarking tests and compare some of these different formulations, it also gives us a little bit of an insight into how different formulations will degrade. And so in this particular case, if you're using oil number 12 here, I would say viscosity is probably your number 1 test that you should be running, because in this case, after 3 weeks in the accelerated oxidation test, the viscosity increased to outside of its isoviscosity grade, so greater than 10%. Which is significant. So and again, I would say this is an exception formulation. The vast majority of formulations, viscosity is not an issue. But again, it's another good reason to do some initial benchmarking tests. And number 6, higher MPC doesn't necessarily mean more oil degradation. So here we have an example of an oil that over the first 9 weeks of oxidative stress, this is what we would expect. The MPC is slowly increasing here. Week 9, it's pretty high. What happened at week 12? It suddenly drops down to 36. So in fact, week 12, this oil is more oxidized, had generated more deposits on the glassware, had a lower RPBOT value. The aminic antioxidants were significantly more depleted. However, this is not represented in the MPC test. And in fact, you can see there's kind of this formation of agglomerates and some more maybe white splotchy splotches here on the patch. Typically, what is most common with if you trend MPC over time to a really to an extreme level, you'll see the MPC will increase, flat, and kind of hit a maximum value and then start to drop over time. So if you're if you're trying to figure out, you're going to buy a filtration skid, a varnish filtration skid, and your MPC is at a 50, and you want to understand how long will it take for the MPC to get down to a 20? You know, it's not actually that's not a simple question because you don't know if the MPC is kind of on its way up or is flatlined or on its way down. The other thing to keep in mind is that the MPC test is measuring color bodies. And, you know, a lot of these degradation products, a lot of the composition of varnish, a big chunk of it is actually antioxidants. Maybe as much as half of these varnish producing compounds are actually depleted antioxidants, and various different antioxidant chemistries will produce different colors. So different formulations will also produce different colors of MPC patches as they degrade over time. So MPC, again, very, very powerful test, great predictive tool for identifying varnish, but higher MPC doesn't necessarily mean higher oil degradation. And number 7, the final one, actually making a really well-balanced formulation is not trivial. And so here we're comparing in the spider chart here 14 different oils, and we're looking at the closer to the bullseye, the better performing product we have. And here we're looking at week 12 of this test. What does the MPC test look like? How high is the MPC? What is the actual varnish production? How does the actual glassware look and actually how much varnish has come out and settled in the catalyst coil in the glassware? So how much varnish has actually been produced? And what's the oxidative stability look like at the end of week 12? What do the antioxidants and the RPBOT values look like? So here we have an oil 14, best in class deposit control. Absolutely no stain at all whatsoever on the patch. It looked phenomenal. However, the antioxidants were chewed up fairly significantly, and we would not expect this oil to last as long as some of the other formulations. Compare this to oil 8, where we have actually a really strong oil life, and we would expect this formulation to last for a long time. And while it's lasting a long time, you shall expect all sorts of deposits to be happening in your system. It produced all sorts of varnish in this case. So actually coming up with a balanced formulation that is balancing long life with very good deposit control is not trivial. All right. Well, I hope that at least a couple of these takeaways that we have learned over the years have been interesting to you. So to conclude, turbine oil formulation can make a significant difference in the performance of the product. Please don't select an oil based on the price of the oil. As you're buying any other asset in your plant, consider the total cost of ownership and consider your oils to be an asset. You should consider them, you know, instead of buying the cheapest product possible, what will perform best in my application, you know, for the life of that product. And also just keep in mind that in this particular case, if you are selecting an oil, you may select oil 8 here, even though it generates all sorts of degradation products, because maybe you have varnish filtration systems on. Or maybe you're a plant that doesn't really care so much about you know, investing in varnish filtration equipment. You want an oil that will last a while without producing any deposits. This may be a totally separate oil. So there's not one best oil in the world for all applications. It really comes down to what oil makes the most sense for your application. Don't base it on price, base it on the total cost of ownership. And one of the ways that you can best understand how an oil is going to perform in service is benchmarking tests. So consider doing something like this. We share this procedure with whoever is interested, and this has been a tremendous learning source for us, and hopefully it will be for you as well. And the last important point that I want to make: if you buy the best oil in the world and you don't take care of it, expect reliability problems. Thank you so much. Been a pleasure to be able to present here again, and hope to see you here at the next session.
Okay, Greg, thank you so much. That was wonderful. And I'm looking at some comments. The comments were just, there was a little concern about data in the beginning, but everything looks like everybody's happy with it. Angus McDonald had fascinating, I can put it up, fascinating data. All these points are, well, you guys can all read that. Hey,
Thank you, Angus.
chat up, anybody has any questions, could add some. I'm scrolling down, but also I just want to include, though Greg is ending here, he will be more eternal in the LRVS because we have panel 2 coming up, the future of formulation technology for lubricants. And also Greg will be, have a pre-record on the introduction of the ISML new varnish badges. And hold on a minute.
I'll just make one comment that I see a couple comments, not enough data. Yes, I would completely agree with you. In the course of 20 minutes, we had limited time. Please contact me. I'm happy to share all sorts of data here with you. And but there's a lot of data that's kind of backed all of this up here. Okay, and then Greg, can you see that this question just came in from Ansuman? If the solid deposit, do you see that, Greg? Yeah, if the solid deposits are high, that will not affect the deposits on the MPC, thereby giving wrong varnish potential. So I think the most important thing is to really understand the limitations of the MPC test. There are in fact some cases where you will have a low MPC. I think maybe the most troubling issue is when you have low MPC values, yet you're generating a lot of deposits in the system. But your point is really good. You may have some cases where you have different formulations of producing various different MPC values. So it's really important to understand, your oil, how that is going to degrade in your specific application, and trending is always better in all cases than just taking a snapshot picture of one sample and comparing it to another. So it's always better to actually trend the data, and through trending, you can really start to see if you see a big increase in varnish potential, it's probably an issue that you need to start to address. Good question. And do we have any other questions? Anybody coming in? Okay, I think we're good. Greg, thank you very much for your time. Enjoy. Oh wait, no, we're not going anywhere yet. We're back on it. Another coming in, slowly making its way across the screen. There we go. Ah, okay. Is the MPC only relevant when the particle count is controlled? Well, so keep in mind that the MPC test was, in fact, in its current iteration, was developed for turbine oils. And in most turbine oils, we see particle counts are mostly controlled. When you see a particle count start to escalate, actually, that could be an early indicator that you have a varnish problem or an elevated MPC, especially that 4 micron code. If that starts to become elevated, it may indicate that you could have varnish problems. When we transition out of the world of turbine oils into hydraulic and other applications, this is really where it's important to understand the particle count and the MPC value. And in many cases, we can have hard contaminants or inorganic contaminants, other things that are obscuring the patch, creating a color on the patch and not allowing you to fully understand the varnish potential of the fluid. So particle count is super important. But in turbine oil applications, it generally is something that is that is independent, or at least you can get a good varnish potential, even if you have a slightly elevated particle count, or if you have a very low particle count. As we move into other applications, it becomes more critical. Great question out of India. Thank you so much, Shaman. Greg, and we have a comment from Luger right here. Very good, Dr. Quick. Particles will not disappear when heating the sample when they're solid particles. So that's a very good comment. If you want to differentiate between an elevated isoparticle count and you have hard particles, or if you're trying to understand if they're soft particles or these elevated particle count is made up of degradation products, heat the oil up and then rerun your particle count. Very, very good point. Thank you. But if you heat the fluid up, you will dissolve all of the organic soft contaminants back to the oil. Therefore, they won't show up in the particle count test. If you heat it up and the particles don't disappear, well, they're hard contaminants, and in fact is a real particle count. Very good comment.
Okay, and we have another comment. Greg, you're still good? We're still good with time?
Diluting solvents may take away a few varnish particles. Diluting solvents may take away few varnish particles during MPC tests. Well, so the MPC test is actually performed with mixing with a petroleum ether, or a somewhat non-polar solvent, and adding more of this to the oil actually won't have any impact on the MPC value. So sometimes when people are first learning to run the MPC test, it's 50 mils of oil and 50 mils of petroleum ether. You filter it, and then you should rinse a patch with petroleum ether. If you rinse it with 30 mils or 50 mils or 200 mils, actually you're not rinsing away the oxidation products. You're not going to change the color. That being said, if you have a high MPC value and you have a dark stain in the patch, and then you go to you add a strong solvent, a more polar solvent that will dissolve the oxidation products from the patch, if you then place that on top of the patch, you'll see that color disappear. If it's oxidation products. If it's not oxidation products, that stain will stay the same. So this goes back a little bit to the previous question. If you have a dark stain, you want to understand if it is hard particles or soft particles. Doing a rinse with a polar solvent will help. Great question. Thank you.
Greg, we have one other question from Vincent. I'm going to bring this on. Take this off. 2 seconds. There you go. Coming up. Thanks.
With the best advantage of this test in comparison to the dry toast 7873. So the dry toast test is, I think you may be referring to the accelerated oxidation test. So there's a pretty significant difference. The dry toast test, you are weighing the particles on a 0.8 micron patch. Actually, I'm sorry, it's a 1 micron patch, and you're weighing the particles, and and you're basing this on the RPBOT value. So the dry toast test, when the RPBOT value gets to 25% of its initial value, then you need to have a maximum amount of a weight that's generated on this 1 micron undiluted patch. One of the challenges with that is that the reproducibility of the RPBOT test is pretty significant. It's 22% reproducibility up to 1,000 minutes, and we know it's significantly higher for oils with RPBOTs greater than 1,000 minutes. So judging when you're hitting 25% is challenging just because of the reproducibility of the test. The other thing is that this 1 micron patch, actually there's a lot of varnish compounds that are much smaller that are able to be collected when you mix it with a non-polar solvent and filter it through a 0.45 micron. You're going to find much earlier, or it's a much better early indicator of varnish than weighing what you're able to collect on a 1 micron patch. So unfortunately, I think the test could be iterated. In fact, the test, there's a lot of similarities. Both oils are being stressed at 120 degrees. So there are some similarities, but I think the difference is we're not using RPBOT as a end mark of the test, and we're also using actually what's measured in the field, the MPC test, rather than this filtration test that you need a special patch to be able to generate the weight of the patch. Really good question. Thank you.
Okay, I think we won't see any more questions from the attendees, but they were great. Greg, thank you very much for your time. All right.
Thanks so much. Great to see everyone. Okay.
Oh, wait, Greg.
Yep.
Vincent has one more question. Is that okay? We got time?
Of course. Yes.
You got it.
Could be interesting to combine with ruler and MPC. You're absolutely right. Yes, there is a lot of value in if you do the dry toast test with the ruler and the MPC. Now I think you're stressing the oil. You're measuring the RPVOT. You have another method of actually measuring the weight of the contaminants, and you're using what most turbine oil users are using in the field: the MPC test and the ruler test. So, very good point. I could not agree more.
Great. Okay. I gotta keep on doing these premature calling it out, and I think that's it. I think we're good. Greg,
Okay.
thank you very much for your time. And again, everybody's going to be in the introduction to ICML, new varnish badges, and in the panel 2, which is coming up in pretty darn quick. All right.
Okay. Thanks so much, everyone. Enjoy the show.
Thanks, everybody.